Hello and welcome back to CST 3130. So in this lecture I'm going to explain how you can do time series prediction with AWS SageMaker. Okay, so machine learning is a really massive field at the moment. It's complicated, time consuming, often highly mathematical. People have kind of specialist jobs, called, data scientists who just do this stuff for their job, yeah. But I'm not trying to teach, the ins and the outs of data science. You probably need to do like a MSc in data science or something for that, yeah. I'm just doing a single lecture within a single module, yeah. But what I am going to do within this lecture is show you how you can use a cloud machine learning service to generate predictions about your data, yeah. So, you don't need a PhD in machine learning to be able to make time series predictions. You just need to understand how a machine learning service works and how to format your data in the appropriate way so you can use that machine learning service, yeah. So that's what I'm going to cover here in this lecture, yeah. Not going to go into any of the mathematical or technical details. I'll point you to, a paper on the deep AI algorithm if you're interested though, yeah? So a little bit of an introduction about machine learning. Then I'm going to talk about the synthetic data. This is like data I've generated for you to kind of check that your machine learning works for this module. Then I'm going to show you how to graph plot on Node. I've already shown you how to do front-end graph plotting, but this is like more sort of used for the kind of exploratory process of machine learning. Then I'm going to introduce AWS SageMaker, which is like the machine learning service on Amazon Web Services. Then we can talk about how you can use this service to kind of train up a model and then use that model to generate predictions about your data. And then at the end, I'll just say a little bit about categorical data. Okay, so there's sort of, long history of AI going back to the 50s. And, as part of that history of AI, people have used, different approaches to learn patterns from data sets, yeah? And machine learning is of great interest to AI because obviously it was discovered quite early on that we can't just write, hard-coded rules that determine every little thing, to control a robot's every possible scenario kind of thing, yeah? So the advantage of machine learning is we can use it to generate behavior that's not being explicitly programmed. Yeah, we could, in theory, write some code that would like do face recognition for every possible face of the 7 billion people on the planet, but obviously that would take an enormously long time. Well, so it's much easier if we can figure out a way in which you can train a computer to recognize faces by exposing it to lots of different pieces of data. Yeah. So machine learning has been around for many years, and in many ways, arguably, the recent AI boom as a result of three main factors, right? We've discovered better ways of doing machine learning using deep neural networks. So this is kind of a combination of being able to run these large models. We've got like more computer power for that. But also there's some kind of tweaks and hacks to these large models that make them actually work well in a way that we hadn't figured out like 20 years ago, yeah? So deep neural networks is a big breakthrough that's enabled machine learning to make massive strides in recent years. And these deep networks typically fed by these very large data sets. In many cases, they don't have to be, but often in many cases they are. And these large data sets, have often come from like the web or, big companies like Google or Facebook who have access to large numbers of labeled faces or images or objects and this kind of thing. Yeah. The AI boom's also been fueled by the availability of computer resources to do all this training, partly through cloud resources, but also through GPUs, which enable, much larger models to be trained with larger data sets, yeah? So this has led to, these kind of breakthroughs in kind of face recognition, object detection, this kind of thing, yeah? So, back in the day, people often used kind of what's called simple neural networks, where you had like an input layer, a sort of hidden layer, and then an output layer. And these networks, they could learn some stuff, but it wasn't brilliant, and, no one was that excited by them, even though there was quite a lot of work in that area, yeah? But with deep neural networks, we have multiple layers, and they figured out ways in which they can train these. This is the kind of tweaks and hacks kind of department kind of thing, where we can actually figure out how we can train these deep neural networks so that the sort of early stages of the network learn sort of basic features. If you're talking about images, these might be edges, corners, this kind of thing, yeah? And then as you go further up the hierarchy of the network, then neurons become sensitive to increasingly complex features. And that way, we can train these deep neural networks to do complex tasks like learning faces, and we can also reuse the networks or parts of the networks in order for different tasks, yeah, which also makes things a lot easier, yeah. So now we're in the kind of deep learning kind of revolution, I would say. And most of the AI breakthroughs in the last 10 years have kind of been based on some form of deep learning. Yeah, so now we've got image face recognition is pretty much as good as human performance now. Driverless cars, these are obviously partly kind of algorithmically, we're kind of programming these cars to do certain things, but we're using deep networks to, do things like identify pedestrians and traffic signs and this kind of stuff, yeah? Text processing, so sentiment analysis is an obvious one in the context of this module. We're using a machine learning service, almost certainly based on deep networks, to identify whether people are saying good or bad things within a particular piece of text. But also we've got these networks like GPT-3 and BERT, which are these sort of big language models trained on enormous amounts of data, which can now much more plausibly generate human-like text output. Yeah? In medicine, there's a whole load of work on kind of diagnosing cancer and this kind of stuff using deep networks. Game playing, so DeepMind, based in London, done some very impressive work with AlphaGo, which can now beat the best Go player, and StarCraft and lots of other applications they're building, based on deep networks. Yeah? And robotics, again, not so much at the level of actually deciding what the robot does under certain circumstances, but often we're using deep networks so that the robot understands its environment much better using various forms of classification. Now, machine learning we can apply to lots of different data types. Yeah, we can apply it to images, videos, sound, speech, natural language, categorical get data. Is it a fish? Is it not a fish? Kind of stuff. And what we're going to be focusing on here is applying deep learning to time series data. So time series data is a sequence of data points that start at a certain point in time and are separated by specific time intervals. Usually you can't just have sort of random time intervals, or the network won't make a very good job. I mean, you could, but then it would just be much more complicated. Yeah. So usually time series are, each data point is like 1 hour apart, or 1 day apart, or 1 millisecond apart, whatever is appropriate for that particular domain. Yeah. So this is a classic kind of time interval, right? We've got your month and the price. So month one, the price is $2.27 and so on and so forth. And the idea behind time series prediction is we can use previous values of the time series to predict future values, yeah? And often that's the case, right? If you've got like periodic patterns, for example, you might have sales patterns throughout the year, which maybe spike on Black Friday or spike just before Christmas and around Easter, Valentine's Day, so on and so forth. So if you've got a certain product, it will have a certain pattern over the year. And so the deep network can learn that pattern, and then we can provide some input data with a sort of timestamp on it and say, okay, what's the next series of points after that? Yeah, that's the idea behind deep learning on time series. And that's what we're going to be doing here. Yeah. So we want to predict future values of a time series. So a classic one would be like stock trading or trading on crypto, for example. We want to be able to predict future values of Bitcoin so we can then buy or sell our Bitcoin and make some money. Yeah? So the general machine learning procedure, and again, I'm not going to go into all that here. You will have to do a bit of this for this module, but not enormous amounts. I'm not training you to become data scientists. I'm just giving you a sense of data science and how easy that can be using web services like SageMaker. Yeah. So generally, when you get the data in, it's sometimes, like with crypto prices, it might be absolutely clean. You don't have to mess about. But often with data, you'll have kind of missing values. So previous students on this module have been working with like weather data from certain weather observation stations, going back 100 years. And if it's going back 100 years, wars happen, the station breaks down, and all this kind of stuff. So you end up with missing points in that data that you have to handle somehow. And that's what this kind of cleaning up of the data is. And often with deep learning, we're not doing that here, but often with deep learning, you need to normalize the data, like put it within a specific range so that it's easier for the network to learn it. Yeah. So once you clean the data, got it ready, then we probably want to take a look at it. Yeah, these cleaning and the plotting these stages often take place at the same time. Yeah, any data scientist needs to see what the data looks like by plotting various different graphs of it, so they can understand what it currently looks like, and then they can plan a kind of machine learning strategy for that data. Yeah. So once we've kind of figured out what the data looks like, it's nice and clean, kind of what it's all about, then we can figure out, design a model for that data and then train a model on that data. Yeah. Then there's often a kind of testing, fine-tuning stage. It's a messy, hacky business, data science. So we fiddle around with it for a bit. And then eventually, when we're happy with the model, we use it to make predictions about future values of the data. That's the idea here. Yeah? So, as part of that whole kind of hacky process, people often use synthetic data. Now, synthetic data is a simplified version of data that's expected to occur in the real world. Yeah? So if we've got a new sort of network and we're expecting it to work brilliantly on time series data, then we could just test it on real world data, but we don't really know how well that real world data can be predicted. Yeah, because some real world data is messy and there's lots of different factors involved, and we can't actually make good predictions about future values of the data based upon previous values of the data. So one way to check that the machine learning is actually working is we can just write a bit of computer code that generates some synthetic data, and then feed that into the algorithm and see if it works well on the synthetic data. And then if similar patterns are existing in the real data, then our algorithm should also work on the real data. Yeah? So synthetic data is never completely realistic. It's just a guess about what the data should look like, but because we know exactly what future values of that data look like and what the rules are that are used to generate those future values, we can then see if the machine learning algorithm is picking up those rules and accurately making future predictions. Yeah. So it's often a good idea to check your machine learning algorithm on synthetic data. But obviously the final test of your algorithm should be on real data, because synthetic data is generally a lot easier to make predictions about than real world data. Now, I'm using synthetic data in Coursework 2 for a couple of reasons. The main reason is that the real data that most of you are using for Coursework 2 is going to be very hard to make good predictions about, yeah? Particularly just by feeding them into a time series prediction algorithm, yeah? So if you consider Bitcoin, a lot of you are doing kind of cryptocurrencies each year, yeah? So if you feed in, for example, the last 10 years of Bitcoin prices or exchange rates against the dollar, for example, and then try and use that time series of previous values to try and make predictions about Bitcoin, almost certainly it's not going to be very accurate, yeah? If it's that easy, every kind of Bitcoin trader on the planet would be making lots of money, yeah? And the reason Bitcoin data, for example, can't be just predicted on previous values of Bitcoin is because there's many factors influencing the Bitcoin price. Yeah, Bitcoin depends on kind of computer resources, chip availability, price of energy, policy of different governments, banning or allowing, crypto mining and so on and so forth. Yeah, and just general sentiment, price of the dollar, economic factors, and so on and so forth. Yeah. So if we just feed just the previous values of Bitcoin into our machine learning algorithm, it's probably going to make bad predictions, yeah? So that means that I can't check whether you're doing the machine learning correctly, because the future values you're predicting about Bitcoin, I can't like wait and see whether they're accurate or not, and even if they were accurate, they'd probably be just kind of lucky, yeah? So instead, to help you learn about the machine learning, I'm going to supply you with synthetic time series data, yeah? And we're going to use that data to make sure you're doing the machine learning correctly. So, because I know that this synthetic data that I provide you with works on the deep AR algorithm. The deep AR algorithm can quite easily find the patterns that are in this data and make fairly good predictions about future values. Yeah. So if your predictions look about right, then you're doing the machine learning correctly. If your predictions look completely off, then something's gone badly wrong with your machine learning. You need to go back, figure out what's gone wrong, get it right, and when you've got it right in the synthetic data, then you'll be in a much better position to do the best possible job on the real data that you've downloaded from web services. Yeah. Now, I've generated individual data sets for each student on this course, yeah, because it's synthetic data, it's very easy to generate a personalized data set. And obviously I'm doing that because I don't want you guys just copy each other's graphs off each other. I'm sure, none of you would sink so low, but in previous years, people have sunk pretty low, yeah? So that's why I'm giving you an individual data set, and you must use your own set of synthetic data for training your model and generating the predictions. And I'll only give you marks for synthetic data machine learning and visualization if you use your own data set. So please don't, bother trying to copy someone else's graph or someone else's model. You have to train your own model and generate your own predictions on the synthetic data, or you will get no marks for that part of the course. Yeah, you're just wasting your time, yeah? So please use your own data set. It's very easy to get hold of, and I'll explain that in a little bit, yeah? So there's 5 marks for using machine learning to generate correct predictions about synthetic data. I'm not kind of measuring the correctness, because as you'll see when you look at the synthetic data, it's pretty obvious whether you've got it right or wrong. Yeah. Then there's 2.5 marks for visualizing the synthetic data. I'll show you how to do that in a bit, and also for visualizing predictions about the synthetic data. Yeah. So all in all, the synthetic data is worth 10 marks. Yeah. So what the synthetic data is, it's an hourly time series, so that each data point is separated by an hour in time. That's completely arbitrary, by the way. I mean, it doesn't really matter, but we can consider it to be an hourly time series, and that makes you need to know what that is, because when you come to calculating the start point in order to generate the predictions, you need to know it's hours rather than minutes, or at least be consistent with that. Yeah. The values have a general tendency to increase over time at a certain rate, which varies with each individual data set. And there's a 24-hour periodic change, so it goes up and down over time. And there's some noise that I've introduced in the data as well, just to make it a little bit harder, yeah? And as I've said, it's randomly generated for each student, yeah? So this is an example of what your synthetic data looks like, yeah? So here we've got time and hours going along the bottom. We've got the value of the data, it doesn't really matter what it is. As you can see, it's kind of increasing over time. It's got this 24-hour periodic fluctuation and an increasing amount of noise in the data, yeah? But it's got a very it's generated by a bit of code, so there's very sort of clear set of rules that are used to control that. So actually, the machine learning algorithm doesn't struggle to pick up those rules, and it can make quite good predictions about future values. Yeah. So for this module, you need to download your synthetic data. Yeah. So there's the link where you download the data. I'll show you how it works in a minute. And all you have to do is replace student ID, or in this case M blah 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 881s I think it is, with your own student ID. And obviously, if you can't get hold of your student data, if it's not available there, I've missed you somehow, let me know, and I'll make sure a set is uploaded for you. Yeah. Now, please, the URL changes every year. I don't re-record this lecture every year. So if you to get the link for this year, you need to follow the link on the course website. Yeah, and I'll show you where it is. You just click on the link, change the student ID, and then you can download your individual data set. Yeah, but please don't try and copy and paste in these links in these slides. These are just examples because the URL does change every year. So this is what it looks like. So when you click on the link, initially it just gives you this 1111, which is like a fake student ID, just to kind of illustrate kind of thing. So there's the student ID, which you replace with your own student ID. And then the data, as I'll explain a little bit, is kind of JSON lines format. So you have it's kind of JSON, but each line is a complete JSON document, or JSON object, whatever you call it. And then we've got a start point. This is the start timestamp of the data. And then the target is an array of values, and each value, so the first value corresponds to the start date timestamp, the second value corresponds to the timestamp plus an hour, and so on and so forth. It's a very compact way of representing it. Yeah, we could obviously have one array of timestamps and one array of values, but in this case, because it's an hourly time series, we only need to provide the start timestamp. We need to know it's an hourly time series, and then all of the subsequent values, we just have to add an appropriate number of hours to get the corresponding time value for that point. Yeah. So let's just do a quick demo, show you how it all works. Yeah, just going to check this thing is still recording. Okay, so let's go into here, and here's the course website. Yeah, so if you go to Coursework 2, spring term, here's the thing, and then you can see here we've got the synthetic data download link here, where you just replace the M with 81s with your student ID. Yeah, so click on the link, and it takes you to the page. I bundle this on Amazon, right, because it's easier. Yeah, and then here you've got the link, right. You just replace this number with your student ID, and it'll give you an individual data set for yourself. Yeah, and here you got the timestamp, the target, and then here's the array of values going off there. Yeah, that's all you need to do is download that, paste it into a file, and then make sure it's JSON lines, and I'll explain what that means in a second. Yeah. Okay. Right, so let's just go into the training testing, and then I'll run through an example of using a piece of some of this synthetic data in order to show you how this all works. Yeah. Now, a very important thing about machine learning is you should not train and test your model on identical data sets. Yeah. Because obviously, if I gave you a bunch of data, right, 100 data points, and I said, learn that data, supposing you could learn 100 points, yeah, and then I gave you the same points and said, okay, tell me what the values are, then without any trouble at all, if you'd learned them, you could just trot out the values, yeah. And machine learning works the same way. If you expose the network to some values, and then you request it to make predictions about those same values, well, it can just learn those values, and that's usually what it does, yeah. So you mustn't ever train and test your model on identical data sets, or you'll get weirdly perfect results, which are completely meaningless. Yeah, and this is called overfitting. Yeah, your model can predict the training data perfectly, but what you really want machine learning is not to be able to predict the training data perfectly. You want it to be able to generalize to similar data that it hasn't seen before. That's the whole point of it, right? We're not doing machine learning just so we have a compact representation of the data. With doing machine learning, so we have a model, and that model can then predict data it's never seen before, because it's managed to generalize patterns within the data that it has seen. Yeah. So typically, if we're doing machine learning, properly, we're going to divide the data into three sets. Yeah, there's like a training set, which is the training set for the algorithm. That's what the algorithm sees, and then we have a validation data set, and this is used to kind of fine-tune the performance of the algorithm. Yeah, so it'll run through a training cycle, then it'll see how well it makes predictions about the validation data set, then it'll adjust the parameters and go back and run another training cycle. And again, so there'll be a cycle in which it runs between training and validation in order to get the parameters and the sort of all the weights in the network kind of set correctly as best it can in order to make the best possible predictions it can about the validation set. Yeah. And then finally we have the test set, which is these figures are very approximate. Yeah. And that's used to actually evaluate the performance of the algorithm. Yeah. So once we've trained it, validated it, we have our final model. then what we want to do is we want to see how well that model actually performs on data that's never ever seen before. Yeah. And so this test data set aside, we never use it using training. The network has never seen it before. And then we actually run our, the test data set through the algorithm, and then we measure the performance of the algorithm on that test set. Yeah. Now, machine learning, like I said, is a complicated field. There's lots of different ways of kind of splitting and hacking and fiddling around with this kind of train validation test split. But the important point to remember is the test data set must be something the network's never seen. Yeah, otherwise this isn't. It's not like a meaningful measure of its ability to generalize, and you're just going to get something that overfits. Yeah. So obviously look into it in more detail if you want to learn how to all the ins and the outs of this. I'm only giving you a very rough picture here. Yeah. Now, explain our synthetic data. So in our synthetic data set, we've got 500 points of data, yeah? And in general, when you're doing your projects, you want to download approximately 500 points per thing you want to predict, yeah? 500 Bitcoin values, 500, stock prices, 500 weather points, whatever it is, because that's the best. SageMaker, the deep AI algorithm on SageMaker works best on around 500 data points. I'll talk later about how you can work with less data, but the easiest thing to do is just get enough data so you can just have 500 points, yeah? And so the deep AI algorithm, which is the one we're going to be using on SageMaker, works well if you train on 400 points and validate with 100 points. Yeah, and it's a little bit confusing because in the deep AI algorithm, as I explained, when we come to actually setting it all up, it actually refers to the complete data set as a test data set, whereas in fact technically I think it's a validation data set. Yeah, but setting that slight verbal complication aside, we're basically splitting the data into 400 tests and then the complete data set for validation. Yeah. And if we really wanted to evaluate the performance of that, we'd actually set aside a completely different set of data and then see how well it performs. In this case, for this module, we're going to evaluate the performance just with a kind of a visual check that the predicted data values kind of look about right and has the right pattern and are increasing in the right way. Yeah, so we're not systematically evaluating this algorithm here. We're just training it up and making sure it makes some sensible looking predictions. Like I said, this is not a rigorous module on machine learning. Yeah. Okay. So that's the synthetic data. Now let's get on to the graph plotting side of it. Yeah. Now, as I sort of emphasized several times already, machine learning is an exploratory, iterative process. Yeah, it's never a matter of just applying a method to the thing, because once you get to the point at which you just can apply a certain fixed method to a certain fixed problem, you don't need the person in the loop anymore. You can just write a computer program that does that. Yeah, but data science is much more hacky than that. You look at the data, you fiddle around with it, you clean it up, you try different network configurations, different parameters until something actually works. Yeah. And that process usually involves a lot of graph plotting, so you can see the results of different experiments that you're performing on the data and come up with the best solution for that data. Yeah. Now, in the previous lecture on data, well, in a previous lecture, I can't remember which one it was, on data visualization, I showed you how you can use Plotly to plot data in the browser. Yeah, we just have the kind of Plotly key, I think it is. Don't need the Plotly key, actually, I don't think. But anyway, we have our Plotly, JavaScript library that works in the front end. We can just use it to easily kind of plot graphs on a front end of a website. Yeah. Well, Plotly is also a good way to draw graphs and working with data in Node. Yeah, because when we're doing machine learning with JavaScript, typically we're working with Node without a front end attached. Yeah, we're kind of writing some code and doing some stuff with SageMaker or some other algorithm. So we're not working within the browser space, but we still need to be able to plot those graphs. Yeah, and nice thing about Plotly is it enables us to do that in a fairly simple way. Yeah. So the way we can use Plotly on Node is we sign up for an account. Yeah. And then you write some code that says plot the graph using Plotly, and this code authenticates itself with your username and your API key, which is what you get by signing up with Node. Yeah. And then when you plot the graph, the graph data and the parameters for that plot are uploaded to the Plotly website, and then it outputs a link, and you can click on that link to see your graph. Yeah. So even though you're just working within kind of console space, if you like, with Node, it'll be able to upload the plot to the cloud. And then you can see that plot by clicking on a particular link. Yeah, so it's quite a nice way if you're doing machine learning, you want to see what happens, want to plot your synthetic data, all this kind of stuff. You don't have to paste it into a browser in order to plot it. You can actually just plot it directly using Node and Plotly. Yeah? And as I'll show you, you can even do that within the cloud. Yeah. So once you've signed up for your Plotly account, you have a space here where the API settings are. You've got API keys here, yeah. And then you can just see your username, and then it'll generate a key for you, and then you have to supply that key so that Plotly can then upload that graph to your account. Yeah. So in this example, I'm going to use Axios, which is like a node library for downloading stuff, and that's going to download for HTTP requests, being technical about it. And that's going to download the synthetic data for one student. I'm then going to plot that using Plotly. And this example, you can run it locally, but I'm just going to run it on AWS Lambda. Yeah, probably easier running locally, but I thought I might as well stick it in the cloud. Yeah. So I'm not going to go into massive detail. I think I'll give you this example with example code anyway. But we need Axios because we need an HTTP client to be able to pull the data from the website, from the web service that I just showed you here. So we provide the URL. Again, this changes every year. You need to put the right one in. You need to put your student ID in. You need to supply the appropriate Plotly username and key. I haven't put it here because obviously it's my key. And then we just create Plotly by requiring Plotly with that username and the key. Yeah. Then we have our actual code for plotting the graph. Yeah. So what we're doing here, I don't know if I've got a here's the sort of more detailed stuff. Is we're pulling the data from that URL that I just showed you, where your individual student data is available. Yeah. And then because the data that I'm providing you is in this kind of SageMaker format already, if you want to plot it, you need to generate appropriate set of X values, because all it comes with is a start timestamp. It doesn't come with a whole set of X values. Yeah. So all I'm doing here is just simply putting a bunch of numbers, like 1 for the first timestamp, 2 for the second. I could put proper timestamps in using moment, but for plotting it in a basic way, it doesn't really matter, because those timestamps are just made up anyway. Yeah. Okay, so I build the X value array, and then I can then so now I've got the X values and the Y values. I can then, just pass them up to Plotly with some parameters if I want, and then Plotly will then generate that plot and output it on the console. Yeah. Oh yeah, when I'm calling plot data, this is my own function, so I should have mentioned. Yeah, so this just has the usual Plotly stuff, exactly the same as the front end stuff, where I provide X value, Y, the type of graph, and so on and so forth. Yeah. And then what it'll do, and then this doesn't really matter much because you should know this already. And then we pass that up to Plotly. We've got Plotly plot here with the data, which I'll explain. We have to sort of manually generate the X values, the options for the graph to make it look pretty. And here we've got a callback function that will then just output the link to Plotly, where I can kind of click on the link or paste the link into a browser and see the graph that I wanted to plot. Yeah. So if you're running it locally, you need to call exports handler. But if you're obviously running in the cloud, it'll just call the handler automatically, so you don't need to have that extra line in. Yeah. Now, if you want to run it locally, it's easy. We just install Axios, using npm. Should know how to do all that already. Yeah. But if we're running it in the cloud, we need to upload the appropriate node modules folder containing the libraries that this code needs to run. Yeah. So what we need to do is we zip it up. Yeah. We upload that zip file into our Lambda function, and then it'll unzip it. So it'll have the index.js if you've included it, and the node modules file as well. Yeah. So then you just upload the zip file, unzip it, and then you can just run it within the cloud. Yeah. And then when you unzip it, it'll look like that. Yeah. And let's just quickly show you how to plot the synthetic data. I'm not going to do every detail, but I'll cover the basics. Yeah. Okay. So this is our synthetic data here. Okay. And in order to plot it, let's see if I've got here we go. Yeah, I think got it here. Yeah. So what I've done, no, that's not it. Let's just see if I've got a function. I'll just show you the basics here. Yeah. So here's my plot synthetic data Lambda function. So if you go on, go on this button here. Yeah, we can do upload from zip file. I'm not going to do it here, but if I go to my file, if I can find the thing, I actually got it in WebStorm. Come think of it. Yeah. So I've already kind of previously, which I'm not going to bother showing you now, I've kind of uploaded, I got this graph plot thing here, where I've got my index. So what you do is zip this up and index up into this graph plot zip, okay? Then you can do upload from file, you select the file, upload it, and when it unzips, you end up with the node modules here, with the Axios, which I needed to download it, plus my index.js, which has the code that I just sort of explained to you. Yeah? Now I've already put the right details in here, so if I click on test, it's the code I've just been through, just shown you here. Yeah, it does time out sometimes. I should probably put a slightly longer timeout on it, yeah. But if you run it a couple of times, it does work. And you can see here's the output here, and we've got this link here. So if we take that link here, this is the link to the graphs that I've got within the my Plotly user space, I suppose. So we take that link, we paste it in, and then here we can see This is the synthetic data, and it starts at what, 100 or something. Hopefully it's right. Yeah, that's right. Yeah, and then it goes up to 450 or whatever. Yeah. So it's very easy to kind of plot this data using Node on Plotly, and as I said, it kind of works both within the cloud, but also within like local code running on Node. I think that'll probably do for that. Okay, so let's move on. So we can see our data, we know what it looks like. Now we want to actually make some predictions about it using SageMaker. Okay, so SageMaker is a sort of cloud service, I suppose, for building, training, and deploying machine learning models, yeah? It's pretty easy. There's a few fiddly bits, and I'll cover those fiddly bits in this lecture, I hope, or at least most of them. And you don't need to know how the deep AR algorithm works or how any other algorithms work. The thing you need to know is what kind of parameters you need to provide to the algorithm to make it work with your data. And you need to get the data in the right format and the right place. Okay, that's the sort of tricky stuff. Okay, but once you've got that right, then it's really just a matter of formatting data appropriately, putting in S3, configuring the algorithm to train it with the appropriate parameters. You train a model, and then you use that model to generate an endpoint, and then you ping that endpoint to get predictions about future values of the data. That's how it works, yeah? And it's kind of the same as if we were using Python locally or something to do deep learning, yeah? We get a model, we train it with data in appropriate format. It's the same idea, but we're just saving ourselves some of the fiddly stuff by using a cloud service for that, yeah? And as I said, SageMaker has lots of algorithms for common tasks, and these even like a third-party marketplace where you can actually buy algorithms from third parties if you want to. I'm going to be focusing here on the deep AR algorithm, designed to work with time series data. I might be wrong about this, but I think this deep AR is also used for the AWS forecast service, which is you can upload like some spreadsheets and it'll generate predictions about the spreadsheets. And it wouldn't surprise me if it was used for their internal kind of stock prediction and stuff within Amazon, but I'm not guaranteeing that that's actually the case. Yeah. So when you look at the list of algorithms within SageMaker, there's a whole bunch of them. Yeah, some very useful, I'm sure. And the one we're going to focus on here, because it's designed for time series predictions, is the deep AR forecasting algorithm. Yeah. And so this is designed to estimate the probability distribution of the future states of a time series. Yeah, so any kind of time series prediction is usually it's not like certain what's going to happen, yeah? But if a good algorithm will give you a sort of range of values within which the future value is likely to lie, yeah? And as I'll show you with the deep AR algorithm, it'll tell you the sort of bottom 10% and the sort of, it'll give you a sort of spread of values, and then you can kind of plot, some of the values within that spread in order to see where the predictions are likely to go, yeah? Based on auto-regressive neural networks, they can kind of keep temporal state, I think, yeah. And we can train it on a single time series, or it'll also handle kind of categorical data where we're doing multiple similar time series, yeah. I'm mainly going to focus on a single time series because that's the sort of simplest case, but I'll mention categorical data at the end, yeah. There's a paper on it that claims to outperform state-of-the-art forecasting methods on several real-world forecasting problems. I mean, I suspect that it doesn't make a huge amount of difference because I fiddle around with some kind of basic kind of TensorFlow stuff on JavaScript, which does a pretty good job of predicting time series. And the bottom line is any time series prediction is going to be limited by the fact that you're only looking at the previous values of the time series, yeah? So there's a limit to the accuracy of any of these algorithms, yeah? But the nice thing about deep AR is we don't need, hundreds of thousands of pieces of data. It'll do pretty well on intermediate and large data sets, or even quite small data sets like 500 pieces, yeah? You can read the paper on deep AR, there's a link to it on the course website if you're interested in more of the details, yeah? Now, a lot of data scientists use Jupyter notebooks, yeah? Because as I said, it's like machine learning is an exploratory, interactive process, and Jupyter notebooks are nice because they let you combine like bits of text that explain what you're doing with chunks of Python that actually do something, and then the graphs that are actually plotted by Python. These can all be wrapped up in the same notebook, so you can kind of work your way through the data, have like a cleaning up section, and then a kind of plotting section, and then some training section, and then more plotting, and so on and so forth. Yeah. So this is a very sort of typical workflow for data scientists. Yeah. And you'll also, I've been to talks at AWS summits where, someone sort of sits at a console and they, fiddle around with their Jupyter notebook, and then behold, they produce some amazing predictions and this kind of thing, yeah? So they are supported by AWS, but don't leave them running because they run on a virtual machine and they just burn through your credit, yeah? They'll cost you like $30 a month at least running a Jupyter notebook on AWS. So if you want to use them, you can use them, but they cost a fair bit of money. You can probably run them locally, but I've never really played around with them much, so I'm not covering them in this module, yeah? So this is a kind of typical Jupyter notebook, right? You kind of, you've got a bit of Python code, explanation of what it does, and if it was a bit longer, we could see the graphs and stuff, and then it executes these chunks of code. I'm not quite sure how you do it. You must press return or something, yeah? But I'm not teaching that here. Instead, we're going to use the SageMaker AWS console to train and deploy our models. Yeah, because the nice thing about obviously using the console and training the models there is we can generate an endpoint, and then we're kind of in the kind of web service space, and then we can kind of ping that endpoint and get predictions that way. You can probably do all that in the Jupyter Notebook, but we're going to use the console here in this lecture. Yeah. So the first stage of the training, we're going to upload the training and testing data to S3. Then we're going to pick the algorithm, configure the algorithm, and train the model. Yeah. And the next stage is we're going to then deploy the model to an endpoint, and then we're going to query that endpoint to get the predictions about what happens next in the time series. So let's focus on training stage first. Yeah. So in this example, it's called train and test, but it really should be called train and validation. But I'm sticking to the nomenclature of deep AR because if you get it wrong, I tried putting in validation and the training broke. So stick to train and test, okay? Even though technically the testing would come later. Yeah. So we start off with a training set, which is data with about 30% of the values removed. And then we got the test set, which is the complete set of data. Yeah. And then, as I said, in my view, as far as I understand it, this should be called the validation data set. Yeah. So the data format is crucial, and you have to get this right or we'll just simply break. Yeah. And the training and test data have to be in JSON lines format. Yeah. And there's a little sort of link to what that means there. But you all know what JSON is by now, right? You've got the kind of curly braces and you've got keys and values, and the keys are in quotation marks and all this kind of stuff, yeah? But a normal JSON document, you can separate it out across lots and lots of lines. It doesn't matter how many return marks or spaces you put in it, it'll always just work, yeah? But JSON lines is different, yeah? Each line within the document has to be a complete JSON structure, you might call it, yeah? Complete JSON object, yeah? So it has to start with a curly brace, have all the keys and values, nested stuff is all fine, all the rest of it, but then it must end with a curly brace at the end of the line, yeah? If you press a return mark within that JSON structure so that it's spread across multiple lines, then it will not work with SageMaker, yeah? So each line must be a complete JSON document or JSON object, however you want to describe it. Otherwise, it will not work. Yeah. Now, the format for deep AR is we have a start timestamp in this kind of year, month, day, hours, minute, second format. And then we have this array of numbers. So, guess what? The synthetic data is exactly in this format already. So you don't need to mess around doing that. But obviously, when it comes to predicting your numerical values, what you get off, crypto compare or some weather service is not going to look like that. Yeah, you're going to have to reformat it using a bit of JavaScript probably in order to get it into the appropriate structure so you can then do the training on SageMaker. Yeah, that's why I'm providing you with synthetic data so you understand what the data needs to look like, so you can then get your data to look like that as well, your real data, and then get the machine learning working correctly. Yeah. So we've got start and target, and then we've got cat, which I'll come to later, but that just means that you can provide categorical data split into like multiple lines if you haven't got enough data to train individual models on each item, each feature, you might say. Yeah. So this is what JSON lines looks like, and I'll give you a little example in a bit anyway. So you have each line of this starts with the curly braces and ends with the curly braces, closing curly braces, yeah? And it's not split across multiple lines. So if you're doing categorical, it'll look a bit like this. If you're doing just one line, like as I'll show in my example, then it'll look pretty much like that, yeah? For the synthetic stuff, obviously, yeah? Now, the first step with and this is true of a lot of stuff within the cloud, is we need to get the data up into the cloud so that other cloud services can access it, yeah? And S3 is the kind of dumping ground where like a file system pretty much within the cloud, where we put the data that we want to do things with, yeah? So we need to upload our training and test data to S3, okay? And we put it in a bucket. And we also need to provide a results folder so that the output, so that the kind of trained model, all the details about the trained model, deep AR model, can all be stored in this results folder. Yeah? So we created buckets, separate buckets, probably wise, rather than trying to have it in your public bucket and all this kind of thing. Yeah, keeping a private bucket just for the machine learning stuff. It's much easier to see what's going on then. Yeah, because you'll probably have quite a few of these files. Yeah, if you're doing like 5 cryptocurrencies, you'll probably have 10 files plus the synthetic data plus the results folder and so on and so forth. Yeah, so better to keep in separate folder for machine learning, separate bucket. And then we upload the training and test data. I'm not going to cover that. You should know that already. Yeah, and then we create a folder for the results. Yeah, pretty easy stuff. Yeah. So I'm not going to, as I said, actually do it because it's pointless. But I am going to show you what it looks like. Yeah. So this is JSON lines format. Yeah. So you see here this is the start of the file, and then this is then the matching brace is all the way at the end here. Yeah. So if I go click on that, it may possibly yeah, it's matching there. Yeah. And I think it's I've called these JSON, but I've got a hunch they should be called JSONL with JSONL, but I might need to check that. Yeah. Okay, so that's a single blob of JSON, and if I sort of start putting return marks in here, for example, then this will not work. It's still valid JSON, but it's not valid JSON lines, yeah? So here I've got the data. Now, you'll probably find it easier writing a bit of JavaScript code to manipulate your data, because you're going to need that almost certainly for your numerical data anyway. Yeah, so you can see here, this is my workspace for machine learning, and I've got an absolute ton of different bits of code to do the different bits, but that's partly because I have to do the teaching stuff as well. But in your case, you can probably going to need to write some code for this. Yeah, personally, I like writing this code in TypeScript, but you're welcome to write it in just straight JavaScript or whatever programming language you want. Yeah, all of the code that runs in the cloud has to be JavaScript. But if you want to write local code in Python to do the data processing, well, that's up to you really, because I only mark you, on the JavaScript code that runs in the cloud. Yeah. Okay. So we got yeah. I mean, just to be clear, yeah. Any kind of code I mark for this project, like any of the machine learning code, has to be in JavaScript. Yeah. But I don't mind if you write a small amount of other code to manipulate the data, because you don't need to submit that anyway. Yeah. Okay, anyway, so this is my original document. Yeah, this is should be 500 points of data, I think. Yeah, and then so that's the original data. Okay, that's timestamp and all this kind of stuff. Yeah, and then we've got we got synthetic 181. I think so I split it into train and test actually. Yeah, so that's the training data. Yeah, goes up to 889, and then the test data. Oh no, so 889. So not that. Sorry. Yep, so I'm getting confused here. Okay, so this is the complete, no, this is the data set for training, I think it is, yeah? Oh no, this is the complete data set, yeah? It goes up to like 1,000 or something like that, yeah? It's just like similar to all the data I've shown you already, synthetic data. Okay, and then you've got the test data set. I think it should actually be called the train sorry, I'm messing this up here, yeah. The train data set goes up to 889, that's right, yeah? So the training data set is a reduced value of the sort of test data set for this in this particular case. Yeah, normally sometimes you have a separate data set rather than an overlapping data set, but this is what deep AR kind of expects. Yeah. So I've just basically sliced off the end of this array and then to make it into my my training data set. Yeah. So that's the data sets, okay? And then here we got, where's my S3? So you can see here, yeah, whatever. Here are my buckets. So I've created a separate bucket for my machine learning. Okay, inside that bucket, I've created a folder for the results. And then I've got uploaded the original data set and then the training data set with a reduced number of values, yeah? And then, so that's kind of ready to go. I've got my data now in the cloud, and now I can pass that data to the deep AR algorithm in order to do the training and, train my model, yeah? Okay. So next step, once I've got the data in the cloud, is to train the model with the data, yeah? So what we do is go into the training jobs part of SageMaker here, and then click on create training job, and then it'll load up this kind of page with a set of parameters and things we need to enter in order to set up the training job, yeah? Now, first thing you need to do, well, give it a name, right? That's easy. But we need to assign the appropriate IAM role, yeah? So if you're, working within AWS Educate, which obviously on this module you are, then you should just use the lab role, the predefined lab role, and provide that role to SageMaker, and then it will work, yeah? Remember, within AWS Educate, you can't actually create new roles or mess around with roles. You just have to work with the lab role, which is usually good enough to do most of the things you want to do, yeah? Obviously, if you're watching this and you're not, part of my module and just trying to learn how to do it, then you'll have to create an appropriate role in order to train SageMaker. Otherwise, you need to give the right permissions to SageMaker so it can do what it needs to do, such as access S3 and this kind of thing, yeah? So next thing we want to do is specify the algorithm, yeah? And here we want to do time series forecast with deep AR, so it's pretty easy, yeah? And we're going to use a built-in algorithm. As I said, there's like a marketplace, of algorithms if you, want to get fancy with all this kind of stuff. But here we're just using a simple built-in algorithm, the deep AR forecasting algorithm. So that's what we do. Okay, next thing we need to do is provide, we could specify resources, but don't mess with this, yeah? because the permissions that are set up with the lab role mean that we can only use certain types of virtual machines to kind of train this thing up on, to do the training and to deploy the endpoint. If you change the default role, it almost certainly won't work. Yeah, and previously with AWS Educate, it was like a bit of a nightmare because the set configured roles didn't work with SageMaker properly, with the machines that you needed to train up the DPO algorithm, and it was like messy. Yeah. But now it works much better, so we just leave all that and don't touch it, basically. Yeah, that's what I recommend, yeah. The next thing it is, which we do need to adjust, is the hyperparameters. So any kind of machine learning algorithm has a bunch of parameters, and we can like fiddle with these to make the training and predictions work best on our particular data set, yeah. If we were working on 100,000 data points, we'd have set the hyperparameters differently from if we're working, in our case, with 500 data points, yeah. Some of the default values are fine, but we need to adjust a few of them as well. Obviously, if we're doing this, as part of your student projects or part of another project, we'd probably be experimenting with these algorithms, these hyperparameters, trying different combinations of them, see what would actually come up with the best predictions, and then we plot a nice ROC curve with different kind of parameters settings in order to find the point that did the optimal predictions. Yeah. So you may need to fiddle with these on your numerical data because they may not work. The ones that work on the synthetic data may not work on the actual real numerical data. So these are the kind of parameters we might need to set. Yeah, so time frequency, in this case working with hours, so that's pretty clear, yeah. And we need to set that correctly because obviously you're going to generate a timestamp for the predictions to generate the predictions, and if that's like messed up because you haven't calculated the hours right, then it's not going to work properly, yeah. So epochs is the kind of number of cycles of training and testing. Yeah, the number of times the algorithm, trains itself on the training data and then it validates itself on the validation data. Right? And how fast it how many cycles it does of that to find the best fit to the training data. Yeah. The context length. So this is how many data points it uses to generate predictions. Yeah. So remember, this is a time series. In this case, 500 points long. So a sensible value is about 100 for that. Yeah. So then it will look at 100 points, feed that into the network, and then use that to generate the next 50 points in this case because I've set the prediction length to 50. Yeah. Now, if you want to look deeply into all these kind of parameters, the documentation link is there. Yeah. So we need to put these parameters into the training job. We got bash. We can ignore the bash size and this kind of stuff. Epochs we can ignore as well. Context length and prediction length we need to set for our algorithm. 20 epochs usually fine. Epochs is kind of a trade-off between how much you want to how much careful fitting you want to do, and how much time you want to spend doing it, and how much computer resources you want to spend on that. Yeah. So get the time frequency right, and the epochs, context length, prediction length. Most of the rest you can just leave. Now we need to provide the training data input to the algorithm, yeah? So it's got this kind of channel name, and these are it's not hard, not a drop down, you have to type this in correctly, yeah? We select file, provide JSON, I think I've got this all highlighted right. And then we need to provide the location of the training data. Remember, this training data is the data minus 100 points in this case, yeah? And then we add another channel, click on add channel. We need to add a test channel. As I said, this probably should be called a validation channel, but anyway, test will do. And then we kind of got JSON data formats, yeah, and then we provide the other data set, which is in this case the complete data set, yeah. And that's about it on the channels. So that's the training and the test, okay. Then we need to provide the location of the folder on S3 where the results will be stored, and then this will be used to generate the model, which we can then use to generate predictions, yeah. Okay, we don't need the checkpoint. And then when it's all set up, we then click on create training job, whatever it is, and then you'll see on the list of training jobs, your training job will appear, yeah, whatever name you've given it, yeah. Now these training jobs take some time, yeah, because it's like booting up, launching up the virtual machines, and then it's grinding away, through all the different training stuff. It takes about 5 minutes roughly, depending on, how busy US East 1 is if you're working on AWS Educate. And if you want, you can kind of click on that, view history, and it'll tell you, what's going on with the training job. Usually, like I said, it's 5 or 10 minutes, yeah? And if you want to, you can also look on CloudWatch and see the progress of the training job. And if it breaks, which sometimes it does because you've got something wrong somewhere, then you can often see some kind of helpful error on CloudWatch about why the training job went wrong, yeah? Or even on this list as well. But CloudWatch obviously has much more detailed logs than just the one that comes in the training job, yeah? So I'm going to try and do this. I'm not going to show you the whole training job thing because it'll take too long, but I will attempt to at least go through the process just to show you how it works, yeah? Okay, So where are we at? Okay, so here we are on SageMaker, yeah, and here we got the training section of that, yeah. And so we click on training jobs, yeah. You can see I worked through a few. I've forgotten why that failed, but never mind, yeah. So click on create training job. Okay, so I've told you I've already got all of my data uploaded in S3, so that's all ready to go, yeah. Okay, so let's do, so I don't know, demo training job. 1 or something, yeah, that'll do, yeah. Remember, we're using lab role. We can't create new lab roles, it's not going to work. Then we do the deep AR algorithm, where it's gone, time series prediction, time series forecast, deep AR, okay, great. Input mode file, that's all fine. Don't mess with the resource configuration, because it will basically break it. So time series is hours, yeah. Epochs, I think it's 20, wasn't it? 20. Context length, I said 100 data points here. Prediction length 50. I've done this a few times. Okay, so all these kind of cells and layers, the defaults are fine. With any kind of machine learning, we might want to fiddle with all that to get better results, but we're not trying to do the data science here. So I don't fully understand some of this stuff here, like number dynamic feet, no idea what that means, but we don't need to know what that means because we're using a service for this, and these parameters need set up by experts in the field, yeah? So we'll set the stuff we need, and we'll just leave the defaults for the rest, yeah? Okay, so now we've got the training channel, and it's going to be a file, and it's going to be JSON content type. Now we need to get the location of this thing. I think I stored it in the slides too. This is the training data, isn't it? Yeah. So it's like a bit like a HTTP resource, isn't it? But it's kind of S3 instead is the resource type, and then it's like the : // and then you've got the the actual location with the bucket and so on and so forth. Yeah. So it's not a public URL. It's like an S3 URL. Yeah. So in this case, the S3 location, this is the training data, yeah. Okay, now we need to add a channel, which is in this case test, right? And again, it's a file, it's JSON. And then I'm just copying off my slides because I was just going to save myself some time here. Okay, so that's the location of the complete data set, yeah. Don't need to add any more channels here. Checkpoint configuration we can ignore. We need to say where it's going to store it. So again, I've saved myself a bit of time here. I'm pretty sure that's right. Yeah. So if this breaks, well, never mind. I have one that works earlier. I've done one that works before. Okay. So that's the output path where it stores all the trained model effectively. Yeah. Okay. And that's all we need to do. Yeah. We need to supply where the results will be stored, the training and test data, adjust the parameters appropriately, pick the right algorithm, and give it a name. Yeah. Okay. And then we click on create training job, and on a good day, so now you've got kind of in progress, okay? If we click on the training job, we can see, this starting. As I said, it'll take a bit of a while to boot up. I'm not going to bother showing you all that, yeah? But if you look, you've got the status within the training job, and if you go into CloudWatch, so we've got, that's Lambda stuff, training jobs here. Now, we may not have one. This is the 8th of November. I'll just show you a previous one because it hasn't got the log stream up and running yet. So if I spend ages here refreshing, it will see it, yeah? But you can see here, this is the one for the previous training job. You see the APOC and, all the sort of, how well it's doing and all this kind of stuff, yeah? Okay? So we're not going to sit here waiting for that. We'll move on to the next stage. And as I said, I'll show you with one that I've created already about the next stages, yeah? Okay, so once the training job's finished, we need to create a model from the training job, and that's dead easy, yeah? And then we use that model to generate predictions. Okay, so that's what I'm going to cover next, yeah? So creating the model is easy, just click on create model and give it a name, basically. Again, use the same lab role, unless you're working outside the AWS Educate space, in which case you have to create an appropriate role for your model, yeah? Okay, so just use the lab role within AWS Educate. So let's just quickly do that. Okay, so I'm just, this is a previous one, same data. And then all I do is I click create model, and I select the lab role and give the model demo synthetic. Can't remember what I've been using here. Demo synthetic model 1, whatever seems sensible, yeah. Give it the lab role. And all this stuff is kind of hard-coded stuff, which we don't need. This is just automatic because it's creating it from, from the results folder and all the rest of it, yeah. So I don't think we need to mess around with any of that stuff, yeah. I think we just create model. We just give it a name and a role, yeah. And so here we can see we've got the demo synthetic model, okay? So we've got our model. Now we're ready to do, the exciting stuff, right? Which is actually make predictions about the future values of the data, yeah? So the training creates a model with a couple of clicks, yeah? And the really nice thing I like about SageMaker is we can use this model to create an endpoint, yeah? An endpoint is effectively a web service. It's not a web service that's publicly accessible unless you mess around entering all the kind of authentication details, which I'll show you how to do in a sec, yeah? But it's basically a web service, and then we ping that web service with an appropriate set of, JSON parameters kind of thing, yeah? And then it will generate future values of the data and return them from that web service, yeah? So this endpoint thing I really like. And the other thing I really like about this is they used to be the case that these endpoints ran on virtual machines, and that meant they burned through credit like crazy. Yeah? You're spending $30 a month to leave the endpoint running, so you had to be really, really careful about shutting the endpoint down when you weren't using it to generate predictions. Yeah, but AWS has got better, right? They released this feature around April this year, at least within the UK. So now we can have serverless endpoints, which means you're not paying for the endpoint. You're not paying to have the endpoint running all the time. You can just set it up, leave it running, but you're only paying for the usage of the endpoint, not for the endpoint just to sit there waiting to be used. Yeah. So please, 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 within AWS Educate, always use the serverless endpoints. I can't emphasize that enough. Otherwise, you'll notice your credit just vanish. Okay, you've only got $100, and if you don't use serverless endpoints and you don't shut them down, that credit will disappear and you'll lose everything. Yeah, well, you won't lose everything if you backed it up, and I can give you some more credits, but that's a real pain. You've got to reconstruct your whole workspace. Yeah, so if you use a serverless endpoint, though, you just leave them running, and it'll cost you almost nothing in terms of your credits to leave those running. Yeah, and then you can have a nice workflow where you get the numerical data uploaded, you reformat the data appropriately, ping the endpoint and get the predictions, and it can be like a real proper, really nice, fully finished data visualization website. And that wasn't really possible last year because you had to keep switching the endpoints on and off. But now we've got serverless endpoints. This is like, we can have a really nice architecture for this, and I'm very happy about that, yeah? So please use the serverless ones. Anyway, I can't emphasize that enough, yeah? So let's create the endpoint, yeah? So the endpoint's a bit of a funny one, yeah? Because there's the endpoint, and then you've got the endpoint configuration, which I frankly don't see the point of, really. But anyway, that's how it works, yeah? So we give the endpoint a name, okay? And then we have to, if you haven't got an existing endpoint configuration, you need to create a new one. Okay, this is a bit fiddly, I have to say, but never mind. So you give the endpoint configuration a name, and then you make sure you select serverless here, not provision. Provision means it runs on a virtual machine, burns up your credit. Serverless, as they've got that wonderful serverless goodness kind of thing. So we'll select serverless, yeah. Then we add our model. Remember, we created the model already here, yeah. And the slightly funny thing you have to do with AWS Educate is knock the max concurrency down to 10, yeah. The default is 20, but when I tried it with 20, it failed and said you don't have permission to have, concurrency of 20 on your endpoint or whatever. It doesn't really matter because you're only going to ping it with a single Lambda function anyway. So just turn that max concurrency down to 10, and then it will work fine, yeah? Then we, so you click on edit the endpoint configure with the production variant, turn the max, set this to 10, and then it will work, yeah? And you can see here I've set this to 10, and now I can create the endpoint because I've got this new endpoint configuration with appropriate concurrency set in it, yeah? And I'll show you how to do it. And then you can see here, I've clicked on create endpoint, and then this is a list of endpoints that are currently in service, yeah? And as I said previously, if I had these endpoints and just let them running away, then it'd be costing me $30 a month per endpoint probably, yeah? At least, yeah? But now I can just leave these running because I know that these are serverless endpoints, so they're not going to cost me credit just to sit there waiting for queries, yeah? And then when you go into the endpoint details, you can see the important stuff you need to know in order to actually ping them to get the predictions. And these are the URL of the endpoint. It's not a public URL, but we can use this. Well, it kind of is a public URL, but we have to use appropriate AWS authentication in order to be able to reach that public URL, okay? And then we have the name of the endpoint, which is what we use if we're writing internal code, and I'll show you both, yeah, in order to ping that endpoint to get the predictions, yeah? So the endpoint is not public, that's not strictly speaking, it's publicly accessible, but if you have the appropriate credentials, actually, I should have rephrased that more carefully. And then we can, because it is publicly accessible, but with the credentials, we can use Postman to ping it, and we can also use just JavaScript with the AWS SDK, and obviously we'd use Python and probably Java to ping it as well if we really wanted to, yeah? Now this is the important thing, okay? The important thing is we need to get the data, we need to send an appropriate data package to the endpoint so that it will generate the appropriate predictions and send them back to us. Yeah, if we get this wrong, it just won't work, yeah? And you have these two fields called instances and configuration. Configuration is just what kind of data I want to get back from the endpoint. Yeah, how many samples, so how many points in the future I wanted to predict. The output types we'll come to, but you can ask for the mean future values to be predicted, or the quantiles, which are like the lower range of values or a higher range of values, and samples is just like some sample of possible future values of the time series. Yeah. And if we're doing quantiles, we need to specify what the quantiles mean, whether it's 0.9 or 0.1 or whatever, what quantiles we actually want. Yeah. So that's the configuration. And the instances should look familiar by now. We have a start timestamp and then an array of values. Yeah. So obviously your start, if you remember going back to the hyperparameters, we're doing the context length, okay, which is how many values we're using to make predictions about future values. Yeah. So if we want to make predictions about, I think I've got a thing here. Yeah. So this is the kind of context length. Okay. So in this case, we're sending the last 100 values of our time series, so we can predict the next 50 values, because that's what we set up with the deep AR algorithm. Yeah. So what we need for the start value here is not the start of your original time series used to train it, but the start value of the chunk of data that we're using to make predictions. Yeah. So in this case, the start timestamp should correspond to this. Yeah. So you need to add whatever it is, 400 hours to the start timestamp in order to get the start timestamp for this prediction you're requesting. Yeah. And then the data that you're sending should be like the last 100 values of your time series, with the appropriate, as I said, start timestamp. So you send it this last 100 values, and then it should generate the next 50 values. That's the idea here. Yeah. So this start value is the start of the 100 values that we're sending, and then these are the 100 values, the last 100 values of the time series. Yeah. Okay, our code configuration, yeah. And then if we send it the last 100 values, then we've asked it to make predictions of 50 values, so then it should send back the next 50 values of the time series. That's the idea here, yeah. So once we send it that, then we'll get back our predictions, which is what we wanted, right? Very exciting. And we're going to get the quantiles, and I'll explain what that means. Okay, so the quantiles are the percentage of observations that are below a certain value, yeah. So if you look at, here's my sort of set of observations, okay, and the 0.1 quantile is actually like the 10% quantile. It means that about 10% of the observations will be less than that particular value, okay, are within it's like the bottom 10%, yeah, something like that, yeah. And then the 90% quantile, or the 0.9 quantile, is the value, 90% of the values should be below, it covers kind of 90% of the values, yeah. You can look it all up if you want to get deeply into the meaning of quantiles. Yeah, samples is they're like just sort of examples of future values of the data. Yeah, okay, and the mean, which is probably the one to plot, probably is the mean, and the 0.1 quantile and the 0.9 quantile. Yeah, and so the mean is like the average future value, average predicted values. Yeah, it's all in like nicely wrapped up in an array. So in this case, it's an array of predictions, but within that array, I don't know why it's really an array, but never mind. And then this is actually a single blob of stuff containing the quantiles, samples, and the mean. Yeah, I guess we could request multiple predictions. Yeah. Okay, I'm just looking at this actually. Oh yeah, because instances configuration. Yeah, I guess if we submitted multiple instances, then we would almost certainly get multiple predictions. Yeah, that's why it's an array. Yeah. Okay, so one way of testing the predictions and getting the predictions is to use Postman, yeah? So you probably must have covered this already previously in the course, you probably used it already, but it's a very nice kind of web testing program. It's called Postman because obviously you can send GET requests using the browser, but sending POST requests is harder because you need to put stuff into the message body, and Postman lets us do that wonderfully and edit the headers and all this kind of fancy stuff, yeah? And the beautiful thing about Postman is it supports AWS authentication. So in that way, we can actually ping protected web services such as our SageMaker endpoint. Yeah, you can just download and install it. So if we want to query the endpoint with Postman, we've got to set it up right. So we provide the URL, which comes from the endpoint. Okay, then we've got the authentication stuff in the auth tab. We need to provide our access key, a secret key. We also need, and I forgot this first time, but you need to do it. You need to supply the region, the service name, and the session token. Yeah, so you need to supply all this stuff so that it can authenticate itself with AWS. And then within the body, select the raw data type and then JSON. And then that blob of stuff I showed you that we pinged the endpoint with, we just need to put it in here, the start, the target, and all the configuration stuff, yeah? And then make sure it's post, well, it doesn't work with get. And then we ping the endpoint, and then we kind of get it, yeah? Okay, so let's run through this, yeah? So we got to the stage of a model, okay? So let's go into this model, okay? So what we need to do is turn this into an endpoint, and then we can query that endpoint with Postman, yeah? So there's not much to see in the model. It's, you know, seems slightly redundant, but never mind. So let me click on create endpoint. So we call this demo. Yeah, okay, so I'm typing past the mic here. Okay, demo synthetic endpoint 1 or something. That'll do, yeah. We're going to create a new endpoint configuration. Okay. I'll just call it, you know, something sensible. These probably have to be unique, yeah. So CFG, okay. And make sure we choose serverless. That's absolutely essential, as I said, because otherwise things are going to go badly. And then we add the model, and let's just go with a. Let's go. I'm not sure if that's trained actually. Let's go with this one. I know this one works. Yeah. Okay, so we're picking a model. Okay. Now remember, we need to change this because within AWS Educate, we can't run something with concurrency at 20, so we'll make it 10. So then we create our endpoint configuration, okay, which is used to configure the endpoint. And then we got the serverless, giving it a name. I think that's all we need, yeah. Okay, so we've got our endpoint configuration with the right concurrency. There's not much to it apart from that, yeah. We can just use the one we've created already, wherever it's gone, this one. Got the name of the endpoint configuration, and then we create the endpoint, yeah. So there's our endpoint. We could sort of wait ages for it to create, but I'm not going to do that now, yeah, because it can take a bit of time to sort of configure itself in the cloud and all the rest of it, yeah. Instead, I'll show you how to ping this one instead, yeah. So this is in service, again, it's in serverless, just make sure that's the case, yeah. So here we have the URL, which we can reach as long as we have the appropriate authentication credentials, and this is what we can reach with code, yeah. So let's focus on the Postman side of things. I think I'm going to cover the code in the next bit of lecture. So here's the URL. Now here's my Postman sort of up and running here. So obviously we put in the appropriate URL there. You can see it's synth to endpoint B, etc. It's post. And if you look at the authentication, I put in the access key, the secret key, you know, the oh yeah, so it's access key, secret key, the region, the service name, SageMaker, and the session token. I think the session token should still be valid. Inside the body, I've selected raw JSON, and you can see here that I've got the target, which is the last 100 values of my thing. This is set appropriately to be the start of these. So this timestamp here matches this value here. Okay, that's very important. Okay, and then configuration, I'm going to get the mean, the quantiles, samples, and these are the quantiles that I wanted to return. Yeah. So I click send. Yeah. Assuming the session key is still working, then off it goes, and it does take a bit of a while. So it's serverless, it's sort of optimized, so if it's not used much, it can take a little while to return something back. But here we go, it's all worked, yeah. So here we've got this back in the body returned by within Postman. We've got the mean and the quantiles, and I don't know if I asked for samples or not, but yeah, and some samples, yeah. Okay. So that's kind of worked with SageMaker, yeah? And we'll sort of see what this data looks like in a little bit, yeah? We can also query this endpoint with JavaScript, yeah? So obviously Postman's good for testing and for the synthetic data, but for your numerical data, in an ideal world, every time you uploaded new numerical data in a proper architecture, then we'd have some kind of Lambda function that would reformat it into, and then get the last 100 values from DynamoDB, ping the endpoint, get predictions, and then store the predictions somewhere so then you could see the current predictions, yeah? To use JavaScript, we use the endpoint name, not the endpoint URL, unless you want to fiddle around with Axios, yeah? And it's the same idea, right? We kind of, we use the AWS SDK, we build this data structure exactly the same as we did with Postman. And then what we do is we have the parameters, like any kind of AWS service. We've got like endpoint name, body, content type, accept, a few bits and bobs, okay? And then we're using the AWS runtime, which enables us to interact with SageMaker using JavaScript code, yeah? Okay, and then with that runtime, we can use to invoke the endpoint using these parameters. This is a callback function. We could also use promises if we wanted. And then if it breaks, obviously, we can, output some error code. Otherwise, we can just output the what comes back from the response of the endpoint, yeah? So I'm going to give you this example code supplied, I think, so I'm not going to talk you through every line, but it's pretty straightforward, yeah. So now where's my function gone? Synthetic endpoint, I called it, yeah. So as usual, this has to have the lab role, yeah. So this is the code here. So again, I've got my endpoint data exactly the same as we did with Postman. The endpoint name here. In this case, we don't need to specify the region because it's running within Lambda, but if it was running locally, we'd need to specify the region. Then we have the parameters for the call, create the runtime, and then ping the runtime, and then we get back the response, and then we can just output it for console, but obviously we could plot it or put it in DynamoDB depending on what we wanted to do, yeah? So again, this may time out because I think I've only got 3 seconds on this Lambda. Oh no, maybe a bit longer actually. It's not quick, but and it would matter if it was quick if we were trying to buy Bitcoin based upon what it did. But in this case, it doesn't really matter because we're just it's just a demo kind of thing, yeah. And the time series is hourly, right? So as long as it comes back within a minute, we're looking good, yeah. So if we go back to where's my synthetic endpoint. So if you want to see, it does give you some output there when I just ran it locally, but just to see the full output, if we just go on the CloudWatch logs, this may be the one I ran earlier. Oh no, it's probably, yeah, it's the one I ran now actually, yeah. So here we've got the predictions, and we've got the means, and so on and so forth, yeah. So we can see within CloudWatch that it's working correctly, we're pinging the endpoint, and we're getting back probably a suitable set of predictions, but to know whether they're good predictions, we have to plot them on a graph, yeah. And this is what we typically get with the synthetic data, and that's why I think this synthetic data is quite good, yeah? So, and if you look at the details of this is plotting the original data and then what comes back from the endpoint, yeah? So the original data is there, yeah? Now you can see here, here in the middle, the mean is this sort of yellowish line going through the middle here. And then the 0.9 quantile means that 90% of the values are below that line there, okay? So that gives you like an upper range for 90% of the values, yeah? And then the bottom range is like, and then 10% of the values are below the 0.1 quantile, okay? So it's giving you the sort of upper and lower bounds of the prediction, which is quite nice, I think, yeah? And then you've got the mean as well. So if I was plotting this data for real or something, for paper, something like that, then I'd definitely do the 0.9 quantile, 0.1 quantile and the mean, because then you can see both the average, but also some idea about the spread of values, because that really matters, right? Because if the quantiles are like way big and way small, then that would be pretty useless prediction. Because it's quite tight predictions, then obviously the system has some confidence in the accuracy of it, yeah? And it should look about like this with your synthetic data, yeah? If it's like way off or like, too high, too low, something like that, you probably got the data structure that you're pinging the endpoint wrong, yeah? You probably got the timestamp wrong, or you probably got the set of values that you're using to ping the endpoint with wrong, yeah? Because this does work with the synthetic data and it should look about like this. And if it doesn't look like this, you're doing something wrong and I'll probably knock some marks off, yeah? Finally, I just want to say a little bit about categorical data. Yeah, so I have found by playing around with it basically that the deep AI algorithm works well with about 400 points or more. Yeah, if it's got a lot less data than this, it may struggle, not work at all. Yeah, so if you can get hold of 500, 400 data points for each of your categories. Yeah, so if you're doing crypto, find 5 prices for 5 cryptocurrencies, exchange rates for 5 cryptocurrencies. If you're doing stocks, pick 5 different stocks. If you're doing weather, find 5 weather features like humidity, wind speed, whatever, within a single location, or the same weather feature like temperature, for example, across 5 different locations like London, Rio de Janeiro, and so on and so forth. Yeah, so get those 500 points if you can. Yeah. And train a separate model for each type of data. Like I said, it doesn't cost you any money to run an endpoint, so you're going to have 5 different endpoints, 1 for each of your features, yeah? Okay, that's the ideal scenario, and will work best and be the easiest to handle, yeah? But with some kinds of data, particularly football data, I found, it can be a bit harder to find 100 data points for each category, yeah? And so what you can do instead with deep AR is you can train the model with a single data set that contains all of the data, but split into different categories, yeah? And ideally, these data sets, these different pieces of data would all be kind of related somehow, yeah? If they're not related, then it's just going to output junk. If you have junk in, it's going to give you junk out, yeah? So cryptocurrencies maybe would be all right, yeah, because they have some patterns that are the same, but then some patterns are different, right? Because regulations and, people's confidence in different cryptocurrencies varies considerably. So it's not ideal, but if you're stuck with small amounts of data, then you probably have to use categorical training, yeah? So yeah, these are the minimum requirements, yeah? So you need at least 300 data points to train deep AI algorithm, yeah? And each time series must be longer than 80, otherwise it will not work, yeah? And the data length obviously must be greater than the context length plus prediction length. So if you have 80 data points and then the context length is 100, yeah, it doesn't have the data that much context to be able to make predictions at all. Yeah, so data length plus context length in this case, if you've got 80 data points, must add up to 80. Yeah. So I did play with this. I'm not going to do a demo now. I think I've covered enough. Yeah, but with categorical data, you'd use JSON lines format again. But in this case, you have cat here, cat 0, 1, 2, 3, 4. If you've got 4 categories, and then in this case, you can get away with 80 values within each category. And then the train data, 120 values in each category. Yeah. And then the train data, you train it on 80 values per category, and then test it with train data and test it on 120 values in each category. Yeah. And so even though you've only got 120 values per category, it will still mostly work. Yeah. And if you look at the examples, this is like some synthetic categorical data I generated with like 5 different categories, and here are the kind of predictions from those categories. Yeah, so it's not brilliant, right? But it's kind of okay. Yeah, it's mostly capturing the patterns, even though it's working on a vastly reduced data set. Yeah. And then in terms of training, well, context length about 50, because you can't make that it can't be 100 because you haven't got enough context length, plus prediction length must be less than the length of the data. And then, so in this case, 75 is less than 80, so it'll just about work, yeah? And you can see here, this kind of works, but probably because the categorical data, although it has different values, it's actually very similar. It's got the same periodic frequency, yeah? Okay, so, you can look at this. Look at this in the slides if you're working with this, yeah? Okay, so we're kind of done. I know it's kind of quite a lot of stuff, but hopefully that's given you enough information to be able to create your own train a deep AI algorithm to make predictions about time series data. Yeah. So there's 10 marks for training up both the synthetic data and the real data. Yeah, 5 marks per type of data. Yeah. With the synthetic data, the full 5 marks are only available if you generate the correct predictions about the synthetic data. Yeah. Because as I've explained, it does work on synthetic data. If you got it right, the predictions should be about right. Yeah. If they're way off, you've done something wrong. Yeah. And to get these marks, any of these marks, you must submit all of your training files, yeah, and code used to generate that training files, yeah. So you must prove to me you've actually done the work by submitting the the JSON lines files used to train it. And obviously, I'll look into your AWS Educate space when I mark this to see that you've got the appropriate models and the endpoints and so on and so forth, yeah. So don't claim you've done it without making it happen within your AWS Educate space, yeah. And then obviously you've got to generate the predictions, plot them on the graph, as well as plotting the original data. Yeah, so I recommend you put them all on the same graph, just like I've done, with the original data and then the predictions, because then it's very easy to see whether the predictions are right or not. Yeah. Okay, so there's quite a few resources for this, including, and obviously I've told you where you can get hold of your synthetic data. And we're done, yeah? So let's just wrap it up, yeah? So I've introduced machine learning with AWS SageMaker, explained how you can use it to make predictions about your time series data, yeah? You practice on your synthetic data set, make sure you understand how it works, get everything right, it should generate the right predictions, and when the results look right, you apply the same method to your real numerical data, yeah? And there's 15 marks available for the machine learning in Coursework 2, yeah?